Yeah, welcome to the 13th lecture, I believe, on causality for AI and ML. And today we will be looking at, I've called it causal perspectives, so frameworks or like other approaches to causality beyond the Pearl causal model that we had so far. And we will keep it rather high level, but I just wanted to show you like other approaches, especially the potential outcome framework, which is like often used in medicine or economics and so on, which we didn't cover in this course. But yeah, maybe we can compare at least their approach, their assumptions with that of Paulian causality. And in the future, if you have to solve some problem on causality, at least you know this thing exists and maybe can choose which framework is best to use there. But let's first start with something on attribution. So last time we had actual causality and considered then responsibility and blame. And the maybe most widely used, or at least researched thing in this direction might be Shapley values. So the question basically is, if I observe some sort of model that takes some decision based on a number of factors, how do I attribute a certain factor for the outcome that I observe in the end? And Shapley values, they come from cooperative game theory. So it's actually if I have a group of players or actors working together, in the end, how do I fairly distribute the payout or the reward that they obtain together among them? And so it's relatively straightforward. You say, okay, I have a set of actors N. They form coalitions, so that are always subsets. And then I have some sort of value function that in the end can tell me for every coalition the reward that I would get or that the players would get if they were to like participate in a game or like perform some sort of action. Yeah, I mean, as we will see, the framework theoretically is quite nice, but there are a few things. So usually they are quite expensive to compute. And this value function here, if you think of it in terms of also causality or counterfactuals, it is required to give me a value for every coalition that I can imagine. But usually, I mean, we observe only one run or maybe repeated runs. But if we are talking about subsets, that's usually a like very large number and factorial, basically. Yep. So the question is, so we assume all the players cooperate. So there is not a player that tries to sabotage the whole thing. Everyone adds to the reward or at least doesn't harm it. So 0 is the minimum value you can assign. And in terms of fairness, we would like to, like very roughly or like abstract, have that we give high reward to actors that increase the reward more, lower to actors that increase less, and so on. And the problem there is that it's usually not like additive in the sense that I can just add all the individual players together and get the final reward, but that there might be like synergies. Certain players working together might add more to the rewards than others, and so on. And formally, what they then define as a fair attribution is this thing first of efficiency, basically saying, okay, if I have the like whole reward of the group, I must like distribute all the rewards value I have. So there is in the end nothing left, no residual or whatever that I didn't distribute. Then, of course, if two players basically act in the same way, then I should attribute them the same. So basically what these Shapley values usually do is they consider some sort of coalition, some subset of the players, and then they say, okay, what is the difference between just a subset without player J or player I, and then the subset with them included. So we will see that later on the slides. That's basically the main idea in the end. And yeah, if this value function for every subset tells, okay, it doesn't matter if I add player I or player J, then in the end they should get the same attribution or reward. And yeah, then something which is more actually about the value function itself, or how I score the players in terms of reward that they add. Maybe it's decomposable, so I can, I don't know, have one function that tells me, okay, all the gold coins collected gives some reward, and the other function tells me, I don't know, have they reached the end, or how far did they get in the level? And we want to have this behave additively or linearly, so there could also be a scaling factor in there. And finally, oh, that went off the slide, but we have a dummy or null player, which basically tells us, okay, if it doesn't matter, it's not good to see, but if it doesn't matter if my player is there or not, so I have a value function of a coalition with and without the player giving the same value, then I don't assign any reward to that player. And yeah, under these four conditions, we would like to find a function that is somehow fair and assigns these rewards. And basically, yeah, as I said before, we usually look at those deltas, we look at particular coalitions, and then get this delta between the coalition with the player minus the coalition without the player, basically, so like how much the player adds there. And these Shapley values are computed like this, and it might look a bit like intimidating, but it's actually, or there's a quite nice interpretation of that, which basically is that if I look at all of the players and I look at all of the permutations I can have, so I no longer have them in a set, but assume they are in some ordered list. And then I just look at every of those permutations and try to figure out, okay, what is the mean reward of some player joining any of those coalitions. So the idea here is on the slides. So we look at some permutation and we consider the actors like joining one by one. And our value function or this delta function, every time a player joins, tells us, okay, how much reward is added, how much reward is added for the second player, and so on, until like we get the full reward for the full coalition in the end. And if we do that, then this formula basically tells us exactly that thing. So we are maybe considering a coalition of only 3 players out of 5. And this set S is this 3-player coalition. And as factorial is basically the way we can arrange all the players like joining before all the rest. And then to even things out, basically to get some sort of normalized expectation, we also have to look at all the other possibilities where these 3 players in the beginning join, and then afterwards all the other players join. But that's some normalizing term. And in the end, I assign then for these 3 players the reward. And as you see, here is this n factorial. So that's that whole thing can grow quite large quite quickly. So there are ways to relax that, but the general idea is really computing the average expectation of a player joining. Yeah, and then it has been shown that these Shapley values, if you compute them like that, are the only function or the only solution to these properties of efficiency, symmetry, additivity, and null players. Yeah, as I said, I just want to show you that all of these things exist. There is quite a lot of literature on that, how to approximate them, how to like handle them under certain conditions and assumptions. But so far, these like basic standard Shapley values, they consider, okay, what a player joins or does not join the coalition. But the problem is if we are looking at machine learning models like neural networks or whatever, I usually have continuous features. And how do I handle that? And the idea is that I still consider these players or actors. So all of my features that I put into my model are now like these kind of players that add to the reward in the end, or maybe a correct prediction. But the value function that I now have, instead of just getting the set of players, I tell it the actual values that go into these features. So this domain of the value function becomes continuous. Basically, it tells me, okay, if I have some sort of observation, maybe I have an image. If I put in like maybe the upper left part and the lower right part, will my CNN or whatever feature predictor or classification model, will it still somehow predict the right thing, or is it off? Does it like do these areas in the image, like maybe they don't contribute to a correct prediction? But then if I have like, I don't know, the lower left corner of the image, then the predictor gets it correct. And the idea here is, yeah, somehow similar to the way it was defined before, although it's like even more abstractly defined. Basically, what we say now is we don't have these standard Shapley values, but they are always conditional on the coalition I'm looking at. And I have this function f, like my neural network, that under some feature input x gives some expected reward. So basically what we are doing, or what this means to intend, is that I look at the whole feature vector and then I marginalize out everything that is not in the coalition. So I, yeah, basically get the average expectation if I only are left with these coalition features, and I like randomize, for example, all the rest. And this can then be written as an integral. Basically, it tells us, okay, I have my value that I get from my classifier or my value function, and I weight it basically by the probability of these features that are not in the coalition, given the evidence that I have. So this S bar given S, this is something we could maybe model with a causal model, or yeah, with a Bayesian network, for example. Yeah.
So we use this method for dimensionality reduction. Say I have a big vector, I only model specific. Obviously, I think computationally, right, it's very, very expensive. So maybe
Yes.
CCA would be a better approach, but like theoretically, that works.
So to use it for dimensionality reduction, you say? I'm not sure. I mean, this integral here, basically, I mean, it reduces dimensionality by marginalizing out all the features that are not in in the coalition, but the problem is, I mean, that's the expansive part, right? It's an integral over continuous variables. And I mean, it's probably like for neural networks or whatever, highly non-trivial how to do this integral, right? So this is super expansive and you need to usually approximate it somehow, but by itself, it's not a dimensionality reduction. It assumes that you can do dimensionality reduction or like really a marginalization. Yeah. Yes. So if we look at that in terms of like graphical models, we could view it like this. So we have all our features and they get fed into this value function in the end. And the standard approach then usually assumes that all those features are independent. But most of the time, like if we have real-world observations, we might observe some causal errors in there. So I don't know, education influences income, influences buying power, and we feed all of those factors into the value function. And the thing now is that, yeah, these Shapley values tend to, yeah, commonly then say, well, income has a direct effect on buying power. So if I include income, I get higher rewards in terms of buying power. If I include education, like without income, it might not increase the buying power. So even though education being a root cause, Shapley values might not attribute it the like full causal strength or attribution that it should receive. And the idea then is that, yeah, we might want to include that into our calculations. And one problem there might also be that, yeah, this independency assumption leads to unrealistic data points because we sample those x's and, yeah, those x's independently when marginalizing out. So also there, our causal structure might help us to reduce the number of cases that we need to iterate over or integrate out in the end. Yeah, slide full of text, but the important thing is, if you remember the formula from before, here instead of a conditional probability, we now just have this do operator. And basically, as I said, we won't go into the details, but it unrolls as you would expect. So instead of approximating the conditional, you now do the interventional probability and do all the rest like before. And yeah, what it then really tells you is that it cuts these upstream links, right? So in the conditional case, the Shapley values also would consider effects in the anti-causal direction that is now removed. And yeah, we can do some further tricks. So if we know, for example, we have a causal graph where xi and xk cause xj, then we might not allow coalitions or like sequences of actors joining that let j join before I and k. So we say, well, no matter what we do, because I and k cause j, they need to come before this j actor. So basically, we are following the way our causal model would evaluate. Right. So this is then related to asymmetric Shapley values. Basically, they again weight all these orderings, all this permutation, and we just say, yeah, well, all orderings of those players joining that do not adhere to the partial order of my causal graph, I assign them a weight of 0, and all the others I assign them, for example, equal weight. And I think that's it for this part. Are there any questions on that? As I said, it will be a rather high level overview this time or this lecture. just wanted to show you some things. Okay, then maybe let's continue with the potential outcomes framework. Sometimes it's called the Rubin-Neyman causal model. And the Paulian causal framework, I think we discussed this last time already. It rather focuses on like general causal effects. It models graphs and so on. But this potential outcomes or Rubin's framework focuses on units, which is basically the participants in your study. So it's really prominent in clinical trials, in medicine, in economics, like these more statistics heavy fields. They usually consider potential outcomes, while the Paulian causal framework usually at least is more like seen in computer science, maybe in physics. So if you go into like hospitals or whatever, the evaluations that they will do there is usually in terms of potential outcomes. Because the thing is, it doesn't help you, as we discussed last lecture, with actual causality. If you have some like, some drugs, some medicine, and okay, on average, it heals your patient, but for this particular patient, it doesn't help. It makes the situation worse or whatever. So they are really thinking about the statistics involved, under which assumptions or under which conditions can I also generalize these causal effects that I see over the distribution? Which kinds of experiments can I also do? Because as we have seen, like doing interventions is often like quite hard, can be expensive, and might even be unethical. So they also come up with like methods or strategies to maybe get some causal effects from observational data. And we will see one of those methods later on. Okay, but of course, like all of those frameworks suffer from the same thing. If we have a patient and we treat the patient in some sort of way, either we can observe the outcome if we treat this patient, or we don't treat him or her and we observe like the natural unfolding, like what happens if we don't give the medicine or the drug, but we never observe both of these terms at the same time. And so the thing here again is, if we want to have causal effects, it's usually framed as this difference between those terms, right? It's this difference between, okay, if I want to be sure that my drug helps, I need to somehow quantify this effect of not giving the drug and like administering it. And the thing here is that I really focus on these individual outcomes. So basically what this means is this YI stands for every possible patient in our study. So is the fifth patient that I maybe, for example, here gave the drug, did he or she become healthy afterwards? Or maybe if I didn't give the drug, had like maybe the patient became healthy anyway. And the question now is, like from all of those observations of individual units, how do I like generalize, and under which conditions can I generalize? Yeah. And basically that's the thing here in our data. We only see one of those, either the treated or non-treated one. And this notation here might be a bit different than to what we've seen before, but basically this means Y is a function of some sort of our treatment. So they usually don't have these explicit structural causal models, because usually it's also quite hard to define them. And they have other conditions that need to be assumed, like as Paulian causality assumes knowledge over the causal graph. They assume some other assumptions and then say, well, under these assumptions, if I treat or not treat a patient, what will be the outcome, basically. So it's still this counterfactual question, and it's more framed in a sort of like missing data problem where I only observe half of the outcomes that I would need. Right. I think we have seen that at some point before, these average treatment effect, at least, that's like over the whole population. These individual causal effects, that's what we would like to like estimate. This in the Pauling framework is then probably closest if we do this counterfactual inference, this three-step procedure. If we have one observation, track back in our causal model, infer the exogenous variables, do some sort of intervention like the treatment, and then forward propagate again. Yeah, and under some assumptions or situations, it might be interesting to look at the treatment effect under some conditions, like under some additional evidence or whatever. Yeah, and really this potential outcomes comes from this counterfactual perspective. I only observe one of those outcomes and what would be the potential, like the switch in outcome or the change in outcome if I now would have switched to the other treatment, like giving the drug or not giving it. Yeah, the same again. Really, if you were to fill this sort of table, it would only like be half full. You know whether you have given the treatment or not. Usually, you know the outcome, and therefore you know whether you observed Y of 1 or Y of 0, but you can never observe both and therefore never observe this difference that you would need. Yeah, and the question then really is, how can I transfer that to like population level statistics? And for that, there are these three assumptions, and this is really then the basis of this framework. So the first thing is this stable unit treatment value assumption. Basically, it's a fancy way of saying, okay, the treatments that I assign to the unit, they don't affect another outcome. So I have trials which are basically independent of each other. So I can still have a strategy how I assign these treatments to different units. But like once I've decided that, like no other unit can depend on the assignment that I made. And then we have ignorability, which is basically this thing we were talking about all the time in Pauling causality. They just more or less say or need to assume, well, if I condition on covariates, so I observe some set of variables, then my statistics are confounded. So basically, it's mostly about randomized trials. So you often read, okay, randomized control trials are the gold standard in medicine or whatever. Basically, what they do is to randomly assign a treatment to different people. And by that, they usually assume that they can factor out like all the confounding, all the stuff that is going on, because like for every confounding value that I have an equal number that get affected in the treatment group and in the non-treatment group. So it's some sort of assumption of, okay, if I average over the treated and non-treated distribution, then all those confounding effects and so on, like factor out and yeah, cancel each other. Which of course, again, is a like quite strong assumptions. And again, there is a lot of work that deals with these kinds of issues. But in the basic case, it's really, okay, if I, yeah, condition on some set of variables, then my outcome and my treatment somehow become unconfounded. And basically, I could use a structural causal model to figure out which sets of variables I would need to condition on. So condition on confounders, do not condition on colliders. So that might also be a point where these two frameworks work together. And finally, we have this thing called positivity or overlap, which basically tells us, okay, within each group, I need to have a non-zero chance of, or the other way around. Every person needs to have a non-zero chance of being in either group. So I will have an example later. Basically, it tells us, okay, the probability of this expression treatment, one given some observation, it can never go to zero. So I need to have support over my whole domain of the variables. So to this stable unit treatment assumption, there are basically two parts. And the first one is this no interference assumption that I told you before. So if I look at all the treatment assignments, the individual outcome should only depend on the individual treatment assignment. And this can like quite easily be violated. For example, yeah, if I get your neighbors vaccinated, then your risk of infection drops too, because you are now less likely to get the disease. And that, however, messes with the probabilities and this assumption. And in the end, again, there are techniques to account for that. But that's like even a very simple case to consider. And yeah, then you have to think about, okay, how do I account for those effects? And the other thing is, in the most simple case, again, that there are no hidden versions of the treatment. So basically, everyone, if I give a treatment, and usually it's taught with binary variables, so either the patient gets a treatment or not, like there are no it's not like a continuous variable or whatever. So then everyone must really get the same treatment, like not different doses of aspirin or like some medication, but really for this assumption to hold, everyone must get the same dose. Again, if we divert from that assumption, then we need to account for all of this and somehow factor it in our calculations. That I think I talked about before. So really, it's this vector criterion or like rather general do calculus thing. Under all my conditioning and so on, do I or am I able to infer the right causal effect? And yeah, finally, so the example here for this positivity thing would be, okay, if I look at the population about like 70, maybe everyone in my data set is a smoker. And that's no problem because I can't build up the necessary statistics to what would have happened if I gave if I gave my treatment to a non-smoker, because now I have no data on that. So that's some assumption which you basically also can't work around. Even the Paulian framework doesn't do much there. It then tells you, okay, you need to make some sort of further assumption, maybe linearity in the effects or whatever to figure out these kind of things. But usually the problem here or the idea here is to set up a study in a way that you don't get this sort of situation. So get enough participants and like diversify and choose your treatment in a way that this situation never happens, hopefully. Yes.
So just get an intuitive sense. Like, I remember when we discussed something similar in the framework, we tried to divide individuals up into groups that were impacted. And we looked at the graph. What we're doing here is just looking at the individuals and pretending that there is no SCM involved in some sense. Okay.
Yeah. Yeah. So that's also like quite heated debate, which kind of framework is better or should be used. Like Yeah, I think the Paulian causal people say, okay, what are you even doing if you don't have a causal graph, right? You need to have some idea how causal effects propagate. And then in this potential outcomes framework, like people say, okay, these graphs, they are always incorrect, right? Like no matter what you do, the world is so complex, especially in medicine or whatever, you have no idea what's going on inside the body. And yeah, we need to make some like more general assumptions, but then if we can settle on them, yeah, that's fine. And you're correct in terms of when we looked at this partial causal identification, there we exactly had the same thing where we looked at individuals and tried to infer some constraint from that. And there we saw exactly this problem, right? That sometimes if we just don't have any observation for a particular group of people, then we just can't solve this equation system because it's like underdefined. So yeah, really this potential outcomes framework, it's super interesting. There is a lot of work. It's also quite old actually, and it's used basically everywhere out of computer science and maybe physics and whatever. Yeah. Don't get confused when you see people talking about causality and using this kind of notation. But now maybe you at least know the assumptions and what can or cannot be done with it. And yeah, so maybe one application, and this again can then be framed in also in terms of Paulian causal models again, is regression discontinuity design. So before we were usually looking at scenarios where we needed interventions to break correlations and so on. And here, these types of methods are called quasi-experimental methods. And basically they tell us, okay, I already have some sort of like observational data set, but can I find some conditions, some phenomena or decisions in this data set which I could like see or interpret as if they were an intervention. And one of those, or the most common example, I believe, is some sort of grant program where you say, well, I want to give grants to students that are excellent. And for the students to be admitted to that program, they need to score like 70 or above in some sort of exam or test. And assume now you are supervising this program and the organization now wants to know, okay, is this thing actually helping or am I throwing money out of the window? Because the thing is usually if I compare groups of students within and outside the program, because that's what I observe, well, it's clear the good students are probably, or they are expected to anyway perform above average. So just making this comparison isn't fair because there is some inherent bias due to these due to the way we select students into or out of this program. And also the rule for the admissions are set. So we cannot intervene. We cannot do a year where we like randomly assign these grants to students no matter their score. So we need to come up with some like other idea. But what we see here is that this selecting a student into or out of this program is some sort of decision which depends on some other variables and maybe even though it's like not a hard intervention in the way that we like independently do this decision, maybe we can still interpret it somehow as an intervention or manipulation of the system. Yeah. And the idea basically is that this cutoff of a test score of 70 is like rather arbitrary, right? I mean, sure, it's maybe the top 20% of students or whatever, but in terms of students skill or whatever, right? You don't expect students that are slightly below this threshold and students that are slightly above it to be like fundamentally different, right? You assume they are somehow similar, and some, maybe by luck or whatever, got above the 70%, and some are below it. And the idea here is that then we don't want to get the total average treatment effect, which also often assumes some sort of linearity and whatever over the whole population, but that at least at this decision boundary, we can observe some sort of treatment effect, which is then really this local average treatment effect around this decision boundary. And the idea here is quite simple. So again, we have a running variable, which is the test score. We have an outcome, which is maybe some long-term performance of the student measured in whatever way. So we discussed this a bit in the fairness lecture also, like how to assess features that I would like to measure but can't measure directly. But let's say we, in some sort of sense, measure that. And yeah, then we look at this area right around this cutoff where students perform above a particular threshold and in turn get assigned this grant or get admitted to the program. And it's maybe, yeah, maybe too simple, but I mean, it under some assumptions that we will discuss later on, the idea is really look at the distribution of students around this cutoff and approach it once from the left, once from the right, and approximate like the expected reward that you get on this left side and on the right side, and do it locally. So don't take the full population, but like, let's say plus or minus 5 test score, all the students there, and see what is the effect of those students, which I assume to be roughly similar in terms of their other properties, their covariates. So if I assume that, then I can say, well, all of the effects that I observe are due to my treatment assignment, due to the additional money or the opportunities they got. And the local treatment effect is then really just the average between those two estimates. Yeah, so in plain words, near the cutoff, the only difference between treated and control is the treatment itself. And yeah, we discussed this. So the thing here is that the rule needs to be a fixed policy, and sometimes it's test scores, some sort of poverty index where you say, okay, below or above a certain threshold, you're poor, you're rich, whatever. But it can also be geographical borders where you say, well, I'm in Europe and maybe I move a few meters to the right across a border to another country. And maybe the people living there, they are quite like similar. They move across the border quite often or settle on the other side and whatever. But still, I have particular laws or rules that apply on at one place or the other. So the effects are not due to the people that I observe there, but due to these laws that like abruptly at some point change. And then, yeah, this thing is this continuity of counterfactuals, basically telling us, okay, this cutoff C, there, I assume all the factors to evolve smoothly, right? So I haven't chosen this cutoff at a particular value where maybe other factors jump suddenly. So usually I assume, okay, maybe age, gender, like things that are equally distributed and where I do not assume that if I go across or above this cutoff, suddenly other factors might jump, because then I would again have this problem to say, well, is the effect I see, is it now from this other factor that suddenly went up, or is it due to my program, or yeah, whatever I do with this decision. And finally, yeah, it's this no manipulation thing. And really, it's if you look at test scores or whatever, you say, well, nobody can manipulate their outcome. They can't like actively choose the side they are in. Like assume all the students have the incentive to perform best and nobody like bribes some teacher or whatever to like get into the program. This can usually be tested. So if you see, well, there is a like particularly large group or like a higher density right beyond this cutoff thing, then there might be, yeah, the idea at least that for some reason, some like students that should not be admitted or have gotten a lower score somehow manage to push their score by some epsilon to get in. Yeah.
Maybe a good example of manipulation would be, for example, if somebody is only allowed to receive a prescription for a weight loss drug above a certain cutoff, and then they can intentionally gain weight to get over that cutoff or something like that.
Yeah. So exactly. So the thing is, you assume that nobody manipulates or acts on their attributes in order to influence this decision, right? So it's maybe then in terms of like intelligent agents or whatever, nobody like tries to manipulate their outcome by inducing additional causal effects among these variables. Yeah. Right. And we might want to draw the causal graph for that. And it's quite simple. And if we look at this, then there could be some sort of like relation to classical vector adjustment. Basically, what we do here is that we say, well, I have this treatment, admission or not, D, and this is now influenced by my X. So it's not an independent intervention or independent variable. From my treatment, I assume some tau that basically then influences the long-term performance. And I have some other factors U that somehow play a role and that might influence the test score performance of my student and the eventual outcome. And the idea really is if you look at this thing from the treatment to the outcome Y, then this path is somehow confounded by those U's. And in terms of do calculus, what I then really do is at a particular point for X, I condition on it and say, well, I assume the effects in the proximity of the C to be roughly equal. So I make an assumption of how Y is composed. And by conditioning on X, I basically log this vector path from U over X to D. Any questions on that? So then just briefly, a thing that comes up from time to time is Granger causality, which is a sort of like more relaxed notion of causality. It can be debated if it's really causal, but sometimes it's at least helpful. And this is usually defined strictly over temporal data, so time series. And it tells me if I can use some signal to obtain information about my outcome, then this is a cause, or at least a Granger cause. Basically, what this tells us, if I hear the rooster crow, it helps me predict the sunrise. But of course, I mean, there is no direct causal relation. So this form of Granger causality, named after the inventor, really is about predictive power. And if we think about Bayesian networks or structural causal models, it's a good criterion as long as we are within distribution. So as long as our statistics don't change, as long as I don't do any intervention or act in the system, then it's because under these conditions, it's okay to basically reason in the anti-causal direction. Yeah, and one thing is, so it not only says, well, I need to have some information, like X does not only need to give me some information about Y, but if we are looking at time series, I can do some sort of auto-regression on Y on itself. And basically, if I'm able to predict Y from its past values and X really doesn't help me anymore, like doesn't produce prediction error, then X does not stranger cause Y, even though I might be able to infer some information of Y from X. And really the idea is that if I look at this time series, I might see some signal in X and sometime later see it in Y. So it's then really about regressing these two things onto each other. And the idea, if we then frame it in a probabilistic way, is okay, do I get the same probability for Y with all of the features that I have, including Xi? Then if that's the case, then Xi plays some sort of role in the prediction or in the outcome of Y, and I say it's a Granger cause. Yeah, then simple auto-regression. Basically, you do two auto-regressions, one of the baseline onto itself or of Y onto itself, fit some alphas, infer some noise, like this is basically the prediction error. And then we do the same thing again. Again, we fit Y onto itself, but now we add this extra term where we fit also this factor or like all of the other time series or particular Xi. And in the end, we are left with some sort of prediction noise. And the idea is if this Xi helps me beyond like the pure autoregression of the baseline, so if these errors are significantly reduced, then I say Xi is a Granger cause of Y. And this testing is then commonly done via F-tests, but yeah, just a side note on that. Right. And again, this notion is really nice because it's so easy to compute. Like you just do these kinds of regressions, do a significance test, and yeah, go with that. And the problem really is that we don't consider confounders. And that was already mentioned like in the first paper, I believe that proposed these kind of things. Soon as we start to intervene, the predictions that we make do no longer hold. So what it does not imply is that I now intervene or act on this X that I identified as a Granger cause, that it will cause Y to change. It just tells me, okay, they are somehow correlated and X gives me some sort of information. And finally, I think it was sometimes mentioned, but usually we looked at acyclic causal graphs because they are nice to compute. You start at the root node and then from there, like compute all the other nodes. But of course, in reality, we usually observe cyclic relations. So this can be in biology, in economy, in climate systems, right? Everywhere where we have feedback loops, so gene regulation or price demand effects in weather systems, basically everywhere we have cycles in our systems. And one might argue that actually cyclic causal models are more common than acyclic ones. Then what you of course can say, well, if I have a really high resolution of my time, I can still observe a lot of effects traversing through the system. Some physical forces need time to propagate, or in economy, maybe prices of some goods are only updated every few minutes. But then if you look at real world physical systems, like some dynamical spring systems and so on, where you have differential equations, there it's not that easy to just unroll the system. Of course, you can always do it and then approximate these cyclic relations, but you always get some sort of approximation error. And it would be better if we had causal models that directly incorporate this, like instantaneous ODEs. And in terms of discovery or causal modeling, of course, we can model cycles within SEM. So it's usually this acyclicity is just an assumption to get some sort of properties, and the standard Markov property and also the topological ordering of DAGs, so that we say, well, one variable comes before another. They break down if we introduce those cycles, because if X causes Y and Y causes X, how do I assign which variable comes first? Yeah. And then also in terms of computing solutions or computing or sampling from these models, it gets more tricky, because before we could sample from our exogenous noise and then step by step go through it. And now we somehow need to find some configuration of X and Y that somehow agrees with both of these equations. So basically, we have an equation system that we somehow need to solve. Yeah. So really, in terms of ODEs, we could say, well, I have some mass spring system and like some weight pulls on the spring and the spring pulls on the weight. And somehow I want to model this via some sort of constraint. And the idea or question now is, what would I say is a valid sample in my SEM? So of course, I can look at the time series, how the whole thing evolves. But if I want to say, well, I want observe a single point in time that is somehow unique to the system, then what I usually do is I try to solve for these equations. So, well, the mass spring system, it swings up and down and so on. And at some point it levels out, it doesn't move anymore. And this is basically this fixed point of the system that then, or this equilibrium point where the forces cancel out, and that basically solves the structural equations. So there we really move from these structural equations to equations that we somehow need to solve, and we're interested in finding fixed points that represent a stable configuration that if we were to set our system to this state, it doesn't move away from it, for example. Then, yeah, just to have it on the slides, discovery on this sort of models is like a big topic. There's a lot of work on unrolled causal models like time series models. And then I look at all of the past values of my system. So this is my variable that I have correlated with its last value, with its value before, and so on. All these values in my time series, they are now somehow correlated. But what I would like to have is not saying, okay, well, from the last value, it's most predictive. Of course, it causes the next value in the next time step of this variable. But what are the factors that lead then to this variation, like that add some delta to the value that my variable had in the last time step? So figuring that out is a bit more tricky. And then also, if I have cyclic models where I really don't consider a time series, but I look at these converged states, for example, then this d-separation criterion that we had before is not strong enough, or it's not suited for these cyclic models, because, well, it assumes basically locality of those conditional, yeah, probabilities on all of these variables. And now if I have a cyclic model, what can happen is, okay, somewhere downstream, whatever that means, I perturb my system, I do an intervention, and the whole system reacts to that. All those effects travel back up, and in the end, again, influence the variable I have intervened on. So yeah, the problem is that basically an intervention is no longer like a local property, but it can basically change the whole system that I'm looking at. And there is this notion of sigma separation, which is a bit more tricky to formalize, but can be done to get similar property to d-separation for cyclic models. In general, then there is a whole range or hierarchy of structural causal models where the innermost classes are causal Bayesian networks and cyclic SEMs. Basically, yeah, only consider conditional probabilities, adding exogenous variables and noise and so on. Then we have simple SEM, which can already involve cycles, but the condition here is to qualify for a simple SEM, it has to be uniquely solvable. So I not only have some set of fixed point, but I have exactly one. Then with modular SEM, this somehow relates to this notion, okay, if I intervene on a system or like marginalize out things, then I don't want all these effects to propagate globally. So modular SEMs somehow restrict the scope of those interventions. And basically they say, well, no matter the order of interventions or how I marginalize variables within those systems, they still have unique solutions, and these solutions also agree with each other. So if I look at a marginalized model, it still gives me the same result as if I were to look at the full model. Yeah. And then we have standard SEMs, which is basically the definition we saw in the first lectures, just that we drop the cyclicity constraint. So this is really arbitrary structural equations between all the variables. We don't really care if they are solvable or not. Maybe there is no solution and so on. And then what we have seen maybe a bit before, in the end, is this broader class of constraint causal models, where in SEMs we still have these structural equations which tell us, okay, some effect propagates from X to Y, so having some sort of order or whatever. These constraint causal models, yeah, they put constraints between variables. So they say, well, variable A is always or equals 5 times B. It's not an assignment. So whether I change A or whether I change B, the effect, like the corresponding other variable, always like reflects that change. It's a hard constraint on my system that usually also might not be intervened because like there is no real notion of a cause and effect in these types of equations or constraints. And really, depending on your problem, what you're working on, you have to choose the right type of causal models. If you can, you probably would like to be inside these cyclic SEMs or simple SEMs because they require more assumptions, but they also give you stronger results. And that's actually it for this lecture. For the next lecture, we will look a bit at research we do in our lab, so in particular meta-causal models, and maybe also something on tractability. Then in the last lecture, have a recap and questions. So we will release probably next week already the exercise exam that you can have a look at it, that you maybe can send us questions. Otherwise, we will recap the lecture and maybe discuss some of the earlier exercises.